I'm not gonna lie to you guys, I have been desperately trying to avoid shooting this video for almost a year. Let's see here. We're not a nanovolt over. But I got myself sucked into a conversation thread here on one of the social media platforms. And the end result of the getting sucked into the thread was just shocking to me, the way this person decided to handle the situation. We got ourselves involved in a thread where a certain company, show that they're both trimmed to exactly 50 volts on the button, a company has had, well, I know of at least 10 different failures with different builders of things. And all this guy does is supply the pallet. And so there was some questions that were raised, and instead of answering the questions or addressing any of the other customers that came up on this thread, this guy with laser focused precision decided that he needed to focus on me. And so he had multiple customers in the same thread saying, hey, mine didn't work. Hey, mine didn't work. I'd like to get my money back. Can we do this? Can we do that? He would totally ignore those people and was jumping spasmodically on me. That happened. I don't take being threatened lightly in any way, shape, or form. I just don't. Well, I've got 3 or 4 of these pallets, 5 of these pallets here that have shown up for people where they're just like desperately, dude, I spent all this money with this guy. It don't work. Can you take a look at it and help me figure out why? Now, I have always tried to hold myself to a higher standard and stay neutral. I don't want to get involved in that noise. I don't. But like I said, this happened. So what I was going to do was I was quietly going to do the repair, and then I was going to go and say, here, this is how we fixed it, have a nice day, and do it quietly from my customer standpoint. But since this happened, that's what's brought us to this position. Now, I don't like being a dick, but when somebody's a dick to me, and it's, well, arguably unjustified, it's like, okay, you chose this fight, not me. And I honestly think a lot of people have never been in a real fight, and I think that if you'd ever been in a real fight, you wouldn't be in such a hurry to get in another. Honest to God. So, we're going to take some time here today. I'm going to parallel up these two 50 amp switchers, and we're going to give it a test run with no modifications to it. And then we're going to come back to it and we're going to clean up a couple different things with it. We're going to change a few things with it. We're going to see what's going to happen. But I'm going to give an unbiased, even though this happened, I'm going to give a fairly unbiased, unpartisan point of view. I'm going to set the gate voltages up the way it's supposed to be done. I've got to change a couple of the terminals on this pallet the way it was delivered to me so we can have proper testing. And then we're going to go forward. So let me get this tied to here. Let me get my power wires built that we're going to need, and then we're going to go play with the pallet. Now let me start here and just remind everybody that it's not my job to talk shit or trash or any of that stuff. I'm not doing any of that. It's just my job to fix, I like to say amplifier, but in this particular situation it's called a pallet. We'll come back to that. And I want to remind everybody that's where I'm approaching this from. So I'm going to show you all my data set points, okay, how we're going to go about establishing our unit of measure. We're going to show you input watt meters, output power, the whole 9 yards. So here we go. We're going to start off with the spectrum analyzer. Our stop point's roughly 150.78 megahertz. Our start point is 0. Okay, now let's pan out. This is a little 12 volt regulated supply. And this is our voltmeter, and I'm going to show you what our gate voltages are. So we've got our gate voltage applied at the moment. We're going to measure here. 1.551. Now we're going to measure here. 1.547. Close enough. We'll shut that power supply down. So we have the same gate voltages being applied to both sets of FETs, okay? And over here we have a 1,000 watt element in peak, 1,000 in average, and our 5 watt element in reverse, back from our Bird 10,000 watt dummy load. This is our voltage showing coming from our power supply into the amp, or into the pallet per se. This whole unit is a pallet. If you choose to purchase one from this guy, what you're going to receive is this copper slab, the board with 2 transistors on it, and in this configuration exactly. It's exactly how it comes from him. This is household Romex cable. This is solid core, I believe 12 gauge, or pardon me, 14 gauge, with an oil resistant coating on it that will break down at about 300 degrees temperature. Okay. Over here we have our amp gauge, our clamp over amp clamp, to show how much current the pallet is going to draw. Over here is our 2 RSP 1500 power supplies, so a total of 3,000 watts worth of power supply. And then to show us input power, we have a 50 watt element here showing us forward. And over here, we have a 5 watt element in reverse showing us a reflag. Well, it's currently in forward mode because I've got to show you how much power we're putting into this thing. Okay, I'm going to try to come back to this exact same framing. So what I want to do is I want to be very transparent, and I'm not too overly interested in saying anything negative about anybody or any business, even though I've been flat out attacked. I have to show from beginning to end what we're putting in the pallet is actually usable data. So right here we're showing you on this meter half a watt. And our top carrier that we're going to put into it is exactly 5 watts. Okay? It's represented by all meters. 5 watts. The same. And now let me show you my principle. This is the signal that we're going to be amplifying from. So if the signal gets changed any from this, going through the pallet, this is 31 dBm down. That's what I have the attenuator on the spectrum analyzer set, and then there's a 20 dB attenuator on the inline decouple pickup, which is over here behind the volt meter. Back there, made by Coaxial Dynamics. If there's any deviation from this signal, rectification, that means we have to go look at our pallet and determine what is causing the out-of-band harmonics. Now this is not like a 2879 pallet. This pallet is very broad-banded based, which means whatever we put into it, it will rectify, and then whatever else it wants to create, the transistor itself is able to rectify RF all the way out into the gigahertz range plus. Okay, so the only throttle stop that you have on the frequency that the transistor can rectify is the pallet itself. 2879 based component, a push-pull bipolar, and that particular platform, a lot of those, they run from 0 or 1.6 megahertz all the way to 30 megahertz. So for them to create anything outside of 30 megahertz is inherently very hard. Okay, because the transistor doesn't want to do that job. This transistor, on the other hand, no matter what you put into it, it can create all kinds of other stuff. So the pallet is the only ability that you have to snub that, short of filtering after amplification process with a low pass and high pass filter, period. So I showed you what our input signal is, and we're going to start out with a ½ watt worth of carrier when we do an energized circuit. Make sure that's all the way down up there. And we're not going to do a modulated test right out the hop. The other thing that we need to take into consideration is each one of these components, it's, quote, a 1500 watt transistor, end quote, and they take a maximum of 5 watts worth of input power per device. Now we're not going to achieve that really big efficiency because the way this pallet is designed and this particular style of transistor mounting, there's some drawbacks to it. We're going to cover that thoroughly here in a few minutes. We'll come back around, we'll talk about the pros and the cons of this pallet versus other ways of creating the board. Less talk, more do. So before we fire it down, once again, here's our ½ watt carrier. Please note, even in the reflect mode, we'll turn our carrier up to 5 watts. It's still showing us 5 watts on this meter. We have little to no reflect coming from the pallet. None. Which is good, which means the input circuitry here is resonant for the frequency that we're putting this on. I am actually technically tuning and running this thing on a commercial frequency for 27 megahertz. Okay, let's turn on our 50 volt supply. We are trimmed to exactly 50 volts as shown here. We're pulling 0 amps as shown here, so the pallet's doing no work, no transformative work whatsoever. Now we're going to turn on our gate voltage. Our gate voltage is now on, and we're going to interject exactly ½ watt. Ooh. We're going to interject a ½ watt worth of carrier, shown here. We're pulling 23.9 or 24 amps worth of draw current from our power supply. We have no input reflect whatsoever, and this is an unmodulated carrier. So we're not overtaxing our supply. Our output power level, remember these are both in 1000 watt increments. Pretty close, within 2% of each other. We're seeing about 500 and say about 25 watts worth of power. And our frequency dispersion looks like this. This is our principal frequency. These are seconds. Second, third, fourth, and fifth harmonics down. This is at 0, 10 dB down, 15 dB down, 20 dB down. Our second and our third order harmonics are only 20 dBs below our principal. Just saying. Just saying. So now let's see how that changes. We can have some frequency stability issues that take place as we go up in drive power. So let's see how much input power this thing requires to make 1,000 watts. So there's a 1,000 watt carrier on our output meters over here, and we are putting just a hair over 1.5 watts. I'd say 1.7 watts in. Our power supply is sitting at 48.7 volts, and we're pulling 34.5 or 34.8 amps worth of current. Now, to do double blind verification, because I don't want to have this involved in the circuit while doing the testing, 1.52, 1.547. It's close enough. At 1,000 watts worth of carrier, this is exactly what our signal looks like. Okay, since I'm not interested in detonating the pallet, we're going to stop for a minute. And what we're going to do is I got to place a fan on here. Let me show you why. This is our output core. This was at 0 when we started. The core is 160 degrees on the output transformer. Our flyback's 151, and the heat sink itself is in the 110 range. That core is at thermonuclear melting down hot, just with a couple seconds of transmission. So to save us from having parts come unsoldered, which we're only about 120 degrees away from that, we need to stop and let everything cool off for a second. We can continue forward. Okay, so we're back. We're going to start out with the same layout as before, but this time I'm going to explain a little bit more in depth of what we're looking at. And sorry, I've spent all day on the phone talking with people about this project and a few others, and my throat's a little hoarse, so just bear with me as we go. Like I said, we're going to use 2 cameras on this particular little clip of video. It was really important to me to show this in a non-cutaway platform. That way the detractors would have 0 legs to stand on as far as saying, oh, he's messing with the camera. I am not. I have no desire or interest in that. And I can re-replicate this over and over and over again as long as the palette doesn't fail. So let me show you the other angle. So now we're on the little 4K camera, and I have it zoomed in on the spectrum analyzer. Our start frequency is 0. Our stop frequency is 154 megahertz-ish. Once again, let's go back to the big camera. Now what I want to do is, first off, I want to show you this camera over here. This little guy, he's right here. And he's zoomed in on this over here. Okay. Once again, now I'm not going to move the big camera anymore, our wide field camera per se. It's going to sit. What I want to show you again is what our input carrier level. None of this is modulated, you guys. There's no input pulses into the carrier. This is just straight up an unmodulated signal input. Okay, let's switch back over to the camcorder, or the handheld. that's our input signal. Let's go back to the big camera. Right down here, we're showing just over a half a watt. It's a 5-watt slug, full deflection. To the right over here is 5 watts. So we're reading the middle scale, dropping the 0. It's just a hair over half a watt. That's what we're putting into this. So once we get started with this test, I'm not going to unkey a whole lot. And if you guys want to sit out there and start a stopwatch, I want to show you how hot this thing gets. Now, right now, let's get some data points. Transformer is at 73 degrees. The bench itself is at 67 degrees. So we've gotten rid of most of our heat from our previous tests. Now, the other thing I want to point out is the way the manufacturer is testing these things is roughly the same way. He has his coax terminuses soldered directly to the pads on the board, input, output, no extra inductor, no extra coax, no relay, none of that other stuff that you guys are going to see inside of a completed amplifier. And all of that affects how the amp works. So this is the amplifier in its most raw form, called a pallet. None of the other stuff. No case, no RF shielding from the case, no extra inductor on the input or output. It's literally straight in, straight on the board, and this is what we've got. Okay, let's bring our power supplies online. Let's get ready to start this key down test. We're at 50 volts on the button. And our gate voltage, once again, has not changed. We'll probe here, 1.54. 1.55. So there's 1/10, 5/100ths of a volt difference between the two gate sources, which is more than acceptable. All right, let's switch back over to the Handycam. This is exactly what we were seeing before. Now, what I wanted to show you is let's continue on with our measurements here. Let's grab our knob and start increasing our window. And we'll start measuring down. I'd say roughly this is our last somewhat noticeable spike in the spectrum. This is our principal operating frequency. All the way down here is what we're actually putting into the amplifier, this here. So all of these other spikes that we're looking at on the spectrum as we go down in integers is not usable RF. Okay? Let me come back around here real quick. Let's go back over to the big camera. Once again, we're only putting 1/2 of a watt. We're pulling 23 amps. We're at 49.9 volts, 8. And we're producing about 600 watts worth of carrier. That is roughly 1/3 of the total, well, it would be 1/4 of the total possible output from this pallet in theoretical form. So let's go ahead, let's increase our signal drive to a total of 5 watts. Okay? Now, let's reach up in here. If I can manage to make it around all the tripod legs. We'll go 2x. Okay, so we're making a 1200 watt carrier with 5 watts worth of input signal. We're pulling 38.1 amps and we're at 49.4 volts. Let's go back to the tripod camera. That's with 5 watts worth of input. That's what the signal looks like. And then back down to our little low 1/2 watt. Please note, the more signal we put into the pallet, the more the signal spikes grow. Okay, back to the big camera. Everything's exactly the same. Now this thing's starting to get so hot, it's smoking. Our flybacks are smoking. 250 degrees and our output transformer is at 200 plus degrees Fahrenheit. We're going to have catastrophic part failure here in a second. from just running the pallet to half of its output potential. It will be nice. We'll put some air on it. I don't want to run it to the ground, you guys. So let me back this up again. We'll put 2 watts in it. There, that's 2 watts worth of carrier, which is making roughly 800 watt dead key. And that's where we'll leave it, with the fan chooching on it to try and keep it cool. Flybacks are still around 200. Our exhaust air temperature off of our heatsink, 117 degrees. And our output transformer at full saturation is at 200 degrees. Okay, so let's get back to the Handycam. Now the reason that this is so important is because we're measuring all of the signal that this pallet is creating across the whole spectrum. All the way up, almost all the way up to 70 centimeters, this pallet is creating noise. Signal that is not usable on frequency. Remember, we're trying to use it in the HF band, which is about 1.6 megahertz all the way to 30. This pallet is 300 times more cross-referent than that. Think about that for a second. Let's just unkey this just for a second. Back to the big camera. 220 degrees. Flybacks at 254. And remember, it's not the pallet design that's keeping this thing alive. It's the spreader, the huge heat sink that's underneath it, and the fact that the parts are ruggedized. That XR, that designation means a lot. Back to the Handycam. So if we're producing 800 watts worth of power to get this reading on the spectrum analyzer, I would probably argue that this is a 250 to 300 watt pallet. And you guys are like, but BBI, you're showing on the watt meter that it's doing 800 watts right now. Right. The only signal that we can count is the stuff that's actually going to be receivable in somebody's radio, which is only about 200 watts of power in this unit of measure. The rest of it is occupied by these other signal spikes. What do you mean? Well, if you're trying to listen to this on the HF band, anywhere in the HF band, this is the only carrier spike that anybody's going to be able to receive. This spike and this spike, which are over half of what our primary principal are garbage. This one, which is roughly 2/3 and 2/3, we have 3 integers of 2/3. So these 3 spikes equal another third one of these. And these here represent one of these in the quantity of signal, total measurement, you guys. We have to look at the total overall output potential. Back to the big camera here real quick. The overall output total is what we have to think about. Now, if I was to take a low-pass filter, remember, low-pass filters, they're for 30 megahertz and below. That means they snub off everything that's above 30 megahertz. They won't let it through. Well, but BBI, you say no. This coupler down here is 2 through 30 megahertz. Yes, it is. That means that coupler is going to accurately read everything you put through it from 2 megahertz on the band to 30 megahertz on the band. Now, there's not a solid wall and it says, oh, 31 megahertz, I'm done reading it. No, it still sees it, it's just not accurate. So what we end up having is 100% signal reading, and then it slowly slopes off in its response characteristics like this. So after looking at the spectrum analyzer and looking at our watt meter, I would beg to argue that the watt meter is seeing everything from about, I'd say 0 all the way up into probably roughly around 100 megahertz. Roughly. The kind of response pattern we're getting out of that at 100 megahertz, very little, but everything through that, up to that frequency, it's going to count as power going forward. It's going to see it. Along in the short. Back to the small camera. knowing what you guys are armed with now is knowledge. This doesn't necessarily make this pallet bad. This just shows me that you need to make sure if you're going to use this pallet that you use a low pass filter and be ready for over half of your output power to disappear. Remember, the way you would measure this is you're going to go back to the big camera. You'd have your RF coming in, RF coming out, low pass filter, and then watt meter. Your low pass filter is going to get smoking hot. You might want to think about putting a fan on it. Just saying. Now, with all this testing and all this key down time and parts smoking, we pulled the fan off, and we got about 2 minutes, 2.5 minutes worth of key down time before we started having catastrophic part failure, which is the flybacks. Now, I can't help but notice these transistors are not soldered to this spreader plate. Myself, with very basic rudimentary tools and temperature probes, have figured out that you can get rid of almost half the heat this pallet produces by simply soldering the parts to the copper. Just saying. That sucker is hot. 222 degrees. This flyback resistor is almost 300. This one here is, once again, 250 to 200 degrees. This core is hot. Our heat sink, we're going to get an erroneous reading because it's a shiny reflective surface. 128. And our spreader, is about 230, somewhere in there. I really wanted to cover core saturation and our permeability issues and what we're looking at with frequency resonance response as far as the spectrum analyzer. I'm going to pull the gate voltage off. We disconnect the power supplies. Now let me give this a good 35 minutes, 40 minutes of cool down time. And then we're going to come back and we're going to beat the shit out this pallet. 5 watts should have been more than plenty to send this thing well over 2,000 watts worth of power. These are two devices that in theory, do 1,500 watts apiece. In reality, what we figured out, even with a pallet like this, many of us that have been active in this game for almost a decade now have made the observation that these transistors, you lose a little bit in your combiners, and you lose a little bit when you put the two pallets together, or the pallet, two devices on one pallet like this. The two devices on one pallet inherently is always ran hot. I'm going to show you how to make it run a lot cooler, but we're going to have to radically change the design of the board. And because the guy that owns this thing says do it, I'm going to do it. And we're going to see what we get. We're going to dive deep into that here in a minute. What you end up seeing with two transistors is you lose about 150 watts per transistor on average. So that 3,000 watt envelope now turns into about 2,500, somewhere in there, roughly. Full chooch. Now, we were working with FM, we were working with AM, not FM here today. If we were using this in the 2 meter realm, let's say, and we were working with an FM solid carrier, I would really strongly suggest or would like to see at least 1,200 to 1,300 watts per part in a 2 transistor configuration. But even at that, that's only with 10 watts of input. Well, I showed it with 5. Now we're going to hook up some other stuff and we're going to push it a little bit further. So let me re-rig for that, and we're going to use a different radio, a completely different input signal. We're going to use an ICOM 7300, and then we're going to go to other HF bands and we're going to see how the response of the pallet is, I don't know, on 80 and 40 and 20. And then we'll have that conversation as well. Okay. So we got both cameras set up once again. Now, let's get our power supplies going. It took us about 30 minutes to cool down. And let's get our gate voltage supply plugged back in. Okay, so now we're running our ICOM. Oh dear Lord. Oh dear Lord. Oh dear Lordy Lordy. Let's reset all of our gauges to make sure nothing times out. Okay. All our gauges have reset. We're going to turn our 5-watt slug around. We're not going to pay attention to that anymore. This is a 25 through 60 megahertz slug, so the data that we get from this is going to be, well, this would be a good prime example. This element technically should not read anything, but yet it's still seeing RF head this direction, even though we're all the way up here. Check this out. So right now we're going to go run in the 80 meter band. Okay? Roughly right in the middle. So now here we are at 80 meters. Lordy, lordy, look at that. What are the chances of that as being a result? If we look at this meter here, we'll see we're putting about 1.5 watts in it. And our 2 through 30 megahertz slug up here is telling me that I've got about 1.5 watts going in it. We're at 49.9 volts. With 1.5 watts going in on the 27 megahertz band, we're pulling 34 amps. Now we're pulling 8.3. Let's look at our output power on our watt meter. Look at that. And last but not least, let's go take a look at our spectrum analyzer. Interesting result, right? Let's go back over to the big camera. Let's start dialing our voltage up, our watts up. See, what is that? A 50 watt element. So we're doing about 4.5 watts going in. 4.5 watts going in, producing about 600 watts of power. So we'll go on up to 5 whole watts. That's our 5 whole watt mark. Let's go take a look at the spectrum analyzer. And back over to the watt meter. So that's our data. 5 watts going in, 30 amps worth of current draw, 49 volts. We're producing 600 watt carrier at 5 watts in instead of 1200 watts, like what we were seeing when we were around the 27 megahertz industrial band. And spectrum analyzer. So let's go ahead and let's do a little bit of unit of measure on this. Stay on the spectrum analyzer for a minute. And let's dial down our frequency. So our last frequency hump with a 3.8 or 3.62 megahertz signal going in is roughly around 144 megahertz, just below the 2 meter band on the output side of the pallet. But man, that's some busy signal up in there, man. I gotta tell you, that's a lot of... So our principle would be this first signal hump all the way down here at the very end. Right there. Not the second, not the third, not the fourth. The fourth order harmonic is actually higher than our principal input frequency. That's interesting. Let's stop here for a second. Let's go back to the big camera. Our output transformer is not nearly as hot. Our flybacks are cooking off at 244 degrees, but our transformer is not nearly as hot. Look at that. Our output transformer is only 137 degrees. That's a little piece of data. What does that tell us? What does that tell us about our frequency that the pallet's designed to operate on? What does that tell us about our core saturation, or otherwise our core's ability to be able to absorb the induced RF upon it, and its response? Okay, let's move on. Okay, we're back. So we're going to skip over 20 meters because it was a repeat of 80, but the harmonics jumped out a little bit further. So we're going to jump right up on into 40 meters. What I'm trying to impress on you guys is that if you purchase this pallet with the intention that you're going to go use it on the HF band and not have your neighbors come try and string you up by your short hairs, I would not suggest it. Even with a low pass filter, remember everything the low pass is going to let you do is from 0 megahertz to 30 megahertz. So all the second, third, fourth order harmonics, all that stuff that's below 30 megahertz, it's still going to be going to the air. Now, if you're using an antenna tuner, that might help you a little bit, but your antenna tuner is going to get hot because it's going to have several hundred watts worth of garbage that's going to be getting caught in it. So this is the same test as before. Let me go ahead and back the camera out here a little bit. This is our exact same test as before. Our core is at 112 at the moment. The pallet is around 100, and our heat sink is about 76. So we're cool enough that we're not going to do any damage to anything. We're going to go ahead and put it right to 5 watts. Now remember, at 27 megahertz, this thing was producing 1200 watts with 500 watts worth of input signal, or 5 watts worth of input signal, pardon me. Pardon me. Oof, dinner's not sitting well. With 5 watts worth of input signal, it was producing 1200 watts worth of power. Unmodulated to straight carrier. So now we're going to put 5 watts in it again. Now once again, we're looking at this meter here. 5 watts. This element here, remember me teaching this to you in the last couple segments. This is a 25 through 60 megahertz element. Now we're at 14 megahertz, so we're getting a little bit closer. We're only 3 watts off. What I'm trying to impress with you on this slug is that yes, they'll keep reading past their rated point. It's not going to be accurate. It's not something that we can use as a volume of measurement, but it's still giving us data saying that the element is still responsive. So from 27 megahertz all the way down to 80 megahertz, we're showing that the element that is not resonant for that frequency is giving us signal response. Okay, let's jump over to the small camera. That's our input signal. Yeah, that's something. I'll pull the microphone over here once again. Let me show you where we're at with our principal carrier. It's going to be right here, this very first spike. The rest of this, the second order, is pretty nulled, but our third order is just as much signal as our primary, our principal frequency. So let's go ahead and we'll start rolling the spectrum out and increasing our field of view again. Yeah, right about there's our last measurable spike. Now we're seeing RF spikes all the way out to 328 megahertz. So we're putting 14.142 megahertz worth of input signal in, and we're seeing RF signal. I mean, it's so far down there in the noise floor that you can barely see it. And what I'm talking about is this repeatable spike that's right here. Boop. Boop. Craziness. So it is what it is. Let's go ahead and let's jump up here, and I'm going to punch some buttons on the old amateur radio here. We're going to go to AM, turn our power level down. Now let's go to 10 meters. But PBI, this has got to be good someplace, right? Okay, so now here we are once again in the 10 meter position. So we're at 28 megahertz. Let's verify that data for you all to take a look at. We're at 28 megahertz. Mic gain's almost all the way off. as low as it'll go. Now remember, 5 watts in on 27 megahertz was producing 1200 watts of power. We're at 28 megahertz and we're putting 5 watts worth of carrier in. Now we can start using this element. Why? Because we're at 28 megahertz, we're in the rated element frequency range. 5 watts in, once again, let's go look at the big camera, is producing what? 800 watts worth of carrier. This is a 1000 watt element, and we're seeing 800 watts. This element, remember, don't forget, we left it in 2x. 5 watts in. Let's take a look at our spectrum analyzer. It looks remarkably like it did on 27 megahertz, but we've now fallen out of the response frequency pattern for the palette. As far as this thing being 2 through 30 or 1.6 megahertz through 30 megahertz palette, I think we debunked that thoroughly. This thing is designed for not the HF band. Its power response pattern has very clearly demonstrated that to us. Now we can take and we can add tuners and inductors and a whole bunch of other garbage to this palette and make it so that its response platform is just that. All across the band, everywhere you want to go. I don't see it in any of the provided literature from the manufacturer. Anywhere. So, while we've got the big HF radio hooked up to the palette, let's see what it does. We're going to stay in a wide shot. That's our 5 watts. There's our 10 watts. We're not even over 1,000 watts of output power yet. There, it's 10 watts on the button. 30 amps worth of draw. 49.5 volts. We're not dipping into the power supply. Too awful hard. Let's look at the spectrum analyzer. Back to the big camera. This should be enough to run this palette to full saturation. We've doubled our input power from 5 watts to 10 watts, and we saw a 400 watt increase in output potential. I don't think I need to say anything more. So here we are back in the 27 megahertz band. Now let me show you what we're putting in this for input drive. So it's a 5 watt slug and reverse back from the palette. It's a 50 watt element going forward. Right about 24 watts, 25, 26 watts. Peak power input. Show you what we're getting out of it. That's a 1000 watt slug on the right in 2x. So the 50 hash mark is going to be 1000 watts. 1000 in average on the middle, meter movement or bird, however you want to refer to it. And a 5 watt slug and reverse back from the bird, 10,000 watt numbing load. Hello, 1 2 1 2 1 2 1 2. Hello. It's making roughly 1200 watts worth of power, or roughly the same amount of power that we were getting out of it with 5 watts worth of carrier input. So we're seeing very, very little change. But then BBR, it's running out of power in the pallet, and it's I'm pulling at straws to try and defend it. Hello, audio 1 2 1 2 1 2 1 2 1 2. Hello 1 2. Voltage barely even dropping. Not even half a volt. Hello, 1 2 1 2 1 2 1 2 1 2 1 2 1 2. Hello. Once again, only 24 amps worth of draw. So let's start pushing it a little bit. Now we're going to stand on it. We're going to put 50 watts. 50 watts into these two devices. Hello. About 45 watts. Hello. Hello. We've come up with 15 watts more of input power. Hello. Zero output potential increase. Zero. Which is the problem that everybody's running into. This thing, everybody's told me the same thing. It's running out, petering out, running out of gas, can't do anything more, won't give us anything more. About 1500 watts. Well, we've thoroughly tested this pallet underneath every possible conceivable thing. Frequency, volts, amps. We haven't messed around with the gate voltage any because we don't want to kill the transistors. Input drive, output. It speaks for itself. This pallet is what it is. This is exactly the way it came from the manufacturer. Now, let's go and change some things and see if we can make it wake up a little bit. But first, I want to sit here and I want to talk about this pallet's design. So the first thing that would be probably really helpful for everybody to get their heads wrapped around is that there's not 2 transistors in this pallet, there's technically 4. Okay? When NXP produced this component, it was a brilliant design from the standpoint that we're going to use 2 transistors inside one device. Transistor A, transistor B, C, and D. There's 2 in each transistor. There's 2 devices in each transistor. So now I don't care how you go about trying to choke the chicken, and this is my biggest problem with this pallet, and they always inherently run hot. This particular pallet design, not this manufacturer, but this idea, is the distance across this transistor to the transformer and this transistor to the transformer is shorter than from the transformer to here. We're already setting ourselves up for failure. And the distance from our input transformer to this trace, this distance here makes this thing run horribly. The RF is not hitting both of the solder pads at the same time. There's a huge mismatch in inductance that's taking place here. There's much more inductor on this side of the circuit and more inductor on this side of the circuit than there is here and here for RF pathways. So if you sit here and you really study this with a FLIR, you'll always see that this particular style of board, where you've got the 2 transistors side by side with each other, these inside transistors will always run cooler. And our outside transistors are going to always run hotter. Okay? It's simple, easy, observable science. We've got to have the signal hit our gates, and we have to have the signal come off the drains and be the same. Now, we could go and modify this thing and cut this trace here, cut it right through here, and then create another trace that went this way and bring it back over. But then you start running into output tune inductor problems, and there's a whole bunch of other gobbledygook that can go along with that. I have found in the 30-some different revs of this that I have built, not this design, but with this transistor, 30-some different board designs, that this works. It never works as well as having one singular transistor, like the design that I like to use that I had DNR Radio assemble for me. I chose to do something like this. I had this board designed for my own use this year. This is a true Bifiler output transformer. This works. And this has a fairly flat response pattern from about 3.5 megahertz all the way to about 28, 29 megahertz. And then it starts to have a pretty sharp roll off on it. True Bifiler. This is type 67, I do believe. But it's purpose-made ferrite. It means much more dense material, which means we don't have to worry about the saturation issue that's taking place over here as much. That, and we're only asking more material to do half the job. I wanted to be able to have the signal that was coming in and going out of the transistor to be exactly the same. Now, you cannot hand cut the traces and make one of these work on a multi-transistor device. If you go and get yourself a CNC machine or hook yourself up some kind of mill and you sit here and you cut each one of these traces out with a computer-driven mill, okay, I'll give you that. But the home gamer with a Dremel, each one of the trace surfaces is unbelievably sensitive. Its overall capacitance and its overall inductor principles as its total surface area have to be exactly the same. These things are twitchy, sensitive, little teenage schoolgirls that are just now figuring out, oh, I got boobs and I got power over men. If you don't have your gate set up just right and you don't have your input just right, these things will explode so fast, it's like popcorn at the fair. Pow! Let's look at this circuit's design. This is an input attenuator. Okay? It's built-in safety. There's no attenuator on this pallet. None. I put enough watts into this thing, and it's because of its inefficiency in design is what kept this thing from exploding, blowing these two parts up. This, on the other hand, has a much higher, sharper response curve. Even with this level of attenuator in it, if you put 5 watts in this device, you are really coming close to everything that it's going to get. 5 watts in will get you 1500 watts out of this transistor with this pallet. And I showed that with the 4-pill design that I did. Enough talking about the DNR pallet. Let's look at this one. The gate voltage is having separate independent trimmers for each gate voltage. Dangerous idea, brilliant in wanting to put it in there, it makes sense, but dangerous. Very dangerous. You could run the same gate voltage trigger for both devices. The only time that that's going to unload, though, and you're going to have a mismatch in gate voltages, is when one of these transistors open, and it's going to snuff the whole thing back and shut it off. So it is what it is. There's a lot of different ways that we're going to go about trying to manipulate this pallet. I'm going to sit down from this point forward in the video. You guys aren't going to have to sit here and watch me tinker with this for like the next, I don't know, 3 hours, 4 hours. But the biggest thing that I have is that this is 50 ohm coax. Okay, let's count the wraps. 1, 2, 3, 4. We're summing the shields of each one of the turns of the coax together on the front of the transformer. We have a solid, complete rear plate. This would be our crossover. This is a 9-to-1. Nine to 1. Now, with it being 50 ohm coax, if we do the math, that would mean it's 3.33 ohms. That would get us to 48, 49 somewhere in there. Or you could do 4 passes at 12 ohm and work the math from the other direction. Or here's a novel idea. we could put wire in there. This is not a bifiler setup. Because of the cut coax, because we're using this as our crossover plate, this is a 9-to-1. I know that I'm probably going to get a little pushback from the guy that built this thing, arguing in the other direction. I don't really care. And believe me when I tell you this, Rob, I really don't care what you have to think about me, young man. Don't care. Remember, this happened. Okay, so where to start? I guess we'll start down here. It's good, we'll point down here for a minute. So, let's start here. This is a 9-to-1 board, what they commonly refer to a transformative 9-to-1 pallet. And it shares a lot of characteristics with what we just got done tackling here. But I want to share with you just a rough, very rough idea of how this works. Okay? So, grab something to point with. This is the actual transformer that was in or on this pallet. We're going to come back to this in just a minute. Now, this here is a filter choke. This has got 50 ohm coax in it, and it's what they call a 1-to-1 choke. Okay? The RF can ride on the shield and on the center conductor, and they make it so that the center conductor touches the shield and the shield touches the center conductor. And its whole idea here is to try and suppress outgoing garbage. It's a suppression filter. Holy shit, does that look burned up? Well, it is. This is another one that I robbed out of a repair that came in here a couple years ago. There's a YouTube video about this out there about how I had to fix the guy's LD MOS pallet, and the transistor was still good. He sent this thing in. He goes, I don't know what happened. I bought it from so-and-so. I was running it, and the thing exploded. This is our output, these two tabs. Okay, this is RF, that's shield and ground. Well, when I first started building these, I bought a couple of these pieces, and I noticed right away that these SMA surface mount capacitors that are all across the board, they had a tendency to get very hot the way that we were running them. And you can see tremendous output power with this style of pallet. It looks really impressive on a watt meter. You turn the spectrum analyzer on and it's horrible. Horrible signal. And it's because the pallet is so broad in frequency response, right? Like this thing, you can literally run it from 0 all the way to 6 meters, but the power that you're producing from 0 to 6 meters is also from 0 to 6 meters. This style of pallet's the first one I ever seen that created a harmonic that went lower than its actual input frequency, which is kind of scary. And look, that's inherent. I mean, that's to be expected. When you've got a part like the BLF 188XR that works from 0 all the way out into the gigahertz range, the component, like I said in the beginning segment, the component will respond to anything, because it's so open. I mean, that's a huge spectrum range, like from 0 to, into the gigahertz range. I think 3 or 1 gigahertz or some shit. Look, when all we're interested in is HF operators is from 0 to 30, right? This little tiny window all the way down here at the very bottom, and then the gigahertz range is way over here on the right. Each one of those little signal spurs is junk that's off frequency. How this works is this is your drain side of life over here, okay? You got your gate on the input, the source is your actual foot of the transistor, and the drain's over here, your output side. This is a crossover filtering choke here. It brings the positive voltage, which is on this tab, and the positive voltage, which is on this tab, and runs it through a couple pieces of ferrite to help keep it isolated from the outside universe. That's what these two chokes do as well, okay? Your 12 volt comes in, and this is to help keep it so it's not resonant. It keeps RF off the positive side of the circuit. There's a whole nother choke that you have to add here and another one here to truly make that happen. And that's what these caps do also, is these are fairly high. These are like 103, 104 caps, and they throw this whole circuit out of resonance. The RF doesn't want to go that way. Remember, RF is like water. It's going to take the path of least resistance at all times, right? So it's going to always go to the signal path that's more resonant. Well, like I said, this one burned up because these caps failed, burned all the traces off. I ended up pulling this pallet off, stuck a new one underneath it, and the transistor was still good. Transistor tested fine, and as far as I know, that amplifier is still out there running. This belongs to a friend of mine, and he, believe me, if he had a problem, he'd call and let me know. Amazed that transistor still worked after this. There is a piece of wire that crosses over from this output transformer and this output transformer. Remember, there's two separate devices in each transistor package, okay? This is 12 ohm coax. This is 12 ohm coax. And the way this works is the RF comes out, gets picked up, and look at how the leads are crossed here in the back. See this? RF comes off this tab and immediately runs over to this pallet, or over to this transformer. See? The shield is soldered to this pad. Same thing on this side, runs over to this transformer here. Shield soldered to this pad. Look at how these are wired. Soldered, soldered, coax, shield, coax, shield. Well, if we look down in here, we'll see the shield here is soldered to this via pad, okay? And this shield is soldered to this via pad. They cross over each other. One here, the other one here, and then thusly we cross them over here as well. The idea is with 12 ohm coax that you can make 4 passes on the total network. And what's 4 times 12? 48, close enough to 50. Then we add a little choke on the output side, little 1-to-1 Ballon suppressor, and you're done. Very simple design. Very simple design. Very, very broad in its response pattern. Very, 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 very broad. This plays off the same principles. This is the one that came out of the amplifier. Now, I was sitting here and I'm counting the wraps. I'm like, okay, so this is facing the 2 transistors. You got 1 transistor on this side, 1 transistor on this side. And I'm counting the wraps. I'm like, 4. Well, that would put it down like 3.3 ohms or some shit, because this is 50 ohm coax. Look at the backside. There's nothing soldered on the backside. Now, I immediately thought, oh, this is like a 9-to-1. It's close. Let me clarify this for everybody. This is a simple way of using, oh, and back to this pallet here real quick. The material makeup of the transformers, these rods here and these rods, very, 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 very critical on their interaction with the coax. Okay, so let's jump back over here. I didn't do the heat resistance test yet on this material, but I would probably bet money that this is type 61 that this transformer is made out of. But it now makes sense. This makes sense to me. Basically 100 ohm wire, go into a balanced 50 ohm load, making a pass, go into another balanced 50 ohm load, making a pass, another 50 ohm load, balanced 100 ohm wire again, true crossover. Your saturation pickup's actually on these 2 leads. This makes sense to me now. Math-wise, this is pretty close, but the reason he's splitting this hair is because this is cheaper to do than this as far as cost and components and ease of in-house manufacture. You'll see that it shares the same characteristics. Shield, soldered, shields, soldered. And instead of having permanently affixed crossover bars in the back, We're just using the whole surface of the transformer. It's brilliant. Brilliant. But not electrically correct for the way that it's designed to be used. As we showed on video, from 80 all the way up through 10, the only place that this particular device is actually truly resonant is around the 27 megahertz band for industrial use, right? That's the loophole that we're jumping through here is, well, the pallet's designed for industrial use. We're not making it so it works for 11 and 10 meters and 12. If you really wanted to make this work, you would use coax like this. This is actual 12 ohm coax, and then I've got 24 ohm coax around here someplace in a box. I couldn't find it. You'd want to make 4 passes with this. And then your impedance would be correct, and you'd probably get a whole lot better response out of the pallet across the full signature of the band. But once again, having a very broad response pattern on your pallet is going to be very inherent to interference and other spurious emissions. That's why you'll hear most guys say, oh, make sure to run a low-pass filter. And they're going to assume that you're going to put the low-pass filter post your watt meter. If you put the low-pass filter, and then watt meter, you'll be gobsmacked on the amount of RF that low-pass filter is actually having to choke out. Because the device is full throttled and it doesn't know where it really needs to rectify RF. Hence the reason that you're able to put so much saturation into the device, so much drive with this particular output transformer on it. Well, I don't like this style. It's very dirty. Yeah, the whole transistor and the whole pallet is very responsive across a wide range of frequency, but it's pretty obvious to me the thing was set up to run around 27 megahertz. So what I did in response to this is I did not want to take this transformer apart. This held no interest to me. I want to keep this. Okay. I'll do measurements on that later. I took one of my transformers and I unsoldered the face and I unsoldered the butt. It's brass tubing directly from the hobby shop. Okay. I cut it to length and I created my own transformer, which is what we started working with and we had unbelievable success with. Okay, I'm not going to use a lot of fancy camera shots on this, just simply because I'm trying to save myself like 4 hours worth of editing work. We're going to go through this like we used to do in the old school days. Actually, let me slide this back a little bit. Okay, so let's go over here. We have a 5-watt slug in forward position. Now, there's 0 input reflag. And I'll demonstrate that once we get into operation. So we're reading this middle scale and we're dropping a 0. Okay? This is input power from the 2950 standard bench radio. This is our clip over volt ampering. It's in DC mode. And I've been over here working on things and talking to you guys for so long that meter has zeroed out. Let me reset the amp ring, zero it out. Same exact bias power supply as yesterday. I'll show the metered voltage on that in a second. And our spectrum analyzer is set up exactly the same, right where we left it yesterday, roughly. As I was messing with things yesterday, I might have changed the frequency width because I needed to do an exact measurement. I think we had that set at 350 megahertz, right? So stop frequency. We'll set this around 350 so it's fair. We got to make a very fair and honest, transparent one-to-one comparison between the two. We don't have a choice. We can clearly see it starts at 0, stops at 350 megahertz. Okay, so let's go on back down here for a second. And I'm going to control the amplifier instead of switching off and on the gate voltage. I'm going to switch on and off the actual power supply. So 1.550. Close enough. Close enough for the girls I go with. That'll change as the transistor starts to heat up and do its job. I'm going to need my FLIR, so let's get that started up and get a baseline measurement for it. So we're at 68 degrees out here at the moment. Everything is cold. Okay? So let's make sure I got all my switches set properly. I do. Let's go over here and add validation to what we're using for units of measure. It's a 1,000 watt slug and peak, 1,000 in average or bird, and a 5 watt slug back in reverse from the bird 10,000 watt dummy load. Same 20 dB on coupler, everything's the same. Except I'm not going to show you a peak meter on this side just for space. I think we're going to put like 15 watts into this peak power. About 3.5 bird average. Yesterday we showed definitively on video that even with 10, 15, and 20 watts worth of input, this device, the way it was built, hit an unbelievable brick wall around 1,1600 watts. And that has been the issue with all of the people that have contacted me, is that they can't get it to work the way it is suggested that it works. Okay? Now I got to leave wiggle room in this for the guy that builds these pallets. I'm just showing you what came in here, and I'm showing you what I did to get it to work the way I understand things to work. Be really clear about that. It is what it is. The first thing that I changed right out the hop was this. That's 12 gauge Teflon, or PTFE wire. And I didn't like having this wire that was on it. It's very clearly not the wire that was on it. Same amount of turns, except this breaks down at like 700 and 800 degrees Celsius, where this nylon coated Romex wire breaks down at about 300 degrees. As hot as this pallet was getting yesterday, I had serious safety concerns about this. This wire here is South Wire E 293.9T UL listed, 12 gauge, 3.31 millimeter CU type thin, or TWN 600 volt gasoline and oil resistant, or AWM VW1, and then I can't read that one letter. It says utility 90 nylon, or TW 75 600 volt. That's solid core, and it's adequate. I mean, this is big enough to carry the current load. I just don't like using this particular style of wire. It has a tendency to break down when exposed to hardly any temperature whatsoever. Like right here, this little solder where I was desoldering it, and it literally melted the jacket. Not critical, not life or death. It is what it is. Just for size reference, this is the transformer that came out. These are exactly the same size. I built this transformer. This is the stock one. All right. I changed it so it's an actual true Bifiler. Now, by doing this, you go and you eliminate the frequency response of the pallet. Instead of from being 0 all the way to whatever the number is in infinite land, we made it so it's resonant for about that much bandwidth. Now, even with this style of transformer, I have to say that if you guys choose to try and experiment with this, I want to put a word out there for the whys. 1, use a low-pass filter. 2, you want to make your power supply just big enough for your load. You want it to be able to capitalize on the crowbarring protection of the power supply if your pallet starts to pull too much current. This took a long while for me to figure out. I used to be the kind of guy, oh, it needs 40 amps worth of current? Cool, let's put a 100 amp supply on it. Well, a lot of burned up parts later, not on this pallet. I'm saying in my experimentation days, 5-6 years ago when I was messing with this stuff. you've got to limit your supply to exactly what your theoretical load is going to be. Otherwise, when the thing starts to break down or you have problems, the power supply is going to keep pushing. It's going to allow the transistors to keep pulling, and shit's going to blow up. Well, by limiting the size of your power supply, it starts to draw too much current. I am way more trusting in the crowbar protection and Meanwell supplies that are looking at the current load 50,000 times a second versus me trying to watch the watt meter, watch this, watch the amperage gauge, operate the microphone, all the other stuff that goes along. I'd rather have this click into a safety mode and it says, hey, whoa, pulling way too much current, and shut the device off, versus me watching all the needles go to the corner and then these things light up like Christmas trees. Especially at, I haven't looked at the price, $180 to $300 a piece, depending on which version of this transistor you buy. Oh, I need to drink water. Hold on a sec. Okay. Had to wet the whistle. Every single wire that makes contact with any of the solder pads makes a difference in how the pallet is going to react. So if you have, let me grab a couple new capacitors here. These circuits are very finely tuned on their inductor level and their capacitance level. So let's say I take this transistor and I'm experimenting, let's say. And then I go and I solder it on the board, and I solder it about yay high off the board, and I'm going to get one response. Trim the legs and set it down closer to the board and watch what happens. And also where you actually place the capacitors makes an unbelievable night and day difference in the circuit. Remember, this is not a push-pull transistor. This is not a regular standard by, like 2879 device. This works on its own set of principles, and the way the circuit talks to itself and to the device is completely different. There's a whole different set of rules. Each one of these caps is put in this position for a different reason, to capitalize on its properties and how it's going to tune the pallet to our output source. So you can try and copy this if you want. I would strongly suggest against it until you really understand what you're doing. But yeah, this is way more resonant. The other problem that we had with this transformer was its heating issue. You guys remember that? Just a couple minutes ago, I was showing this thing getting to like 230 degrees. Okay, let's go ahead and let's establish our baseline. Let's zoom on out. What we have going on here is, this is our RG400 coming from our bird meter. This is our 316 coming from our input bird meter. There is our half of watt. That is our half of watt. And let's get our principal shot. Looks remarkably like yesterday, doesn't it? No seconds, no thirds, no none of that garbage. Okay. Let's come on back down here. We'll take this barrel connector out of play. Now, another word to the wise is that this circuit is specifically tuned for these particular situations, this particular environment. In the real world, you're going to have a relay, input coax, some extra inductor, and some other things that you're going to have to compensate for on the input and on the output. There's no relay on this pallet. There's no output coax, so it's not like we're going directly to a 50 ohm and then going over to a relay, and then we're going to have the airframe relay and all of its inductor, and then back out and then to a coax connector. All of those things have to be compensated for when you go and put this inside of a cabinet. Learning those tricks is another big deal. as far as learning how to put these things together, how to compensate for that. I'm showing you how to maximize what we can get out of this pallet in its particular format, in this configuration, in this particular environment. Okay, so we've got our baseline established. Let's go ahead and let's bring on some volts. Ready? Here's our 1/2 watt input again. Exactly the same. Pulling 28 amps at the moment, shown right here. Pretty close to the same, yeah. 1/2 watt in is making 300 watts worth of power, roughly. Goodbye. Hello, goodbye. Without cutting away, now, if you can remember yesterday with a 1/2 watt of input, this thing was making what I think RF way out into 300 something megahertz. Now we're all the way down at around, I don't know, 50 to 75 maybe at the most. But look at how many dBm that is down from the principal. Talking 40 dBm down, right? Huge difference in the pallet's response. Huge difference in the pallet's response to input power. Now, that all being said, let's come over here and let's take a look at this. So once again, let's modulate this. Hello. So we're putting about 2 full bird into the pallet. Modulated, full 2 bird. We're going to click around, come over here. Now the full deflection, if the meter goes all the way to the right, that's 2,000 watts. Hello. Buried it in a corner again. So now we're going to go to 5,000 watt unit of measure. We're back to reading this middle scale, and we're adding 2 zeros. So the 10 is 1,000, the 20 is 2, the 30 is 3,000. Remember what I said yesterday. If we can get around 2,800 watts out of 2 devices, we're going to call that a good day. Anything more than that, it's just false power. It really is. So once again, hello. 2.5 to 3 watts here. Hello. 2,800 on the output. What are we pulling for amperage? Let's all look together. Hello. Around 42 amps. Roughly the same amount of input power we were pulling yesterday to achieve 1,500 watts of power. What's our voltage dip? Hello. 48 volts. We're well within what the power supply can support to the pallet. Hello. 2,800-ish watts. Now, we don't have an attenuator on this pallet, which it does need. So I have to be very, very careful how much drive I put into this pallet over here. If I go and I put maybe full 5 watts, we'll see another 100 and so watts over here on the output side. Is it worth it? I mean, is it really? We know that a max saturation in this particular configuration, please note, very little changed here on the front side of this pallet. This is all on the output side. What I'm showing you here is with 5 watts of drive, we're seeing very little output performance over here, maybe another 100 watts. And all that extra input power gets translated to heat, because the component can't handle anything more. And where it's handling the heat at is here in your flyback resistors, and they're going to get crazy hot. This is 100% efficiency improvement over the way it was when it came in here. Came in here, showed it everywhere across the entire spectrum, input, output power, the whole 9 yards, 1500 watt Mac device. Changed a couple things, about 40 something percent of the parts, about 80% on the ass end. Didn't do a whole lot with the input side because there's not a lot that needs to be done. Let me do this one test before we wrap this up. Turn the element around, so we're going to look at what our input reflect, otherwise how resonant our input circuit is with no attenuator on it. Pretty scooching good. Pretty scooching good. Only a half a watt. That's pretty darn good. That's actually harder to get right than most people would give credit. Saying. Input side of the board, it's okay. Now, like I said, with this particular pallet design, because our gates and our drains are so far separated, and our input and output transformers, our primary and our secondary output transformers are so far apart, these two inner parts work better than the two outer parts, and that's what's also going to create a ton of heat for you. But to be able to take that garbage that we were producing yesterday and to be able to significantly put a dent in the output, if you were to go and apply a low pass filter to this, you guys can remember, we had signal spike, signal spike, signal spike, signal spike, and they were all the way up here, the top end of things. Spike, 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 and then drop off. This is probably 80% of your power is now on frequency versus probably 10 or 15% as yesterday. I mean, that's what, 10, 20, 30, 40, 10, 20, 30, 40 dBm down is our secondary harmonic. And that we've only got 2 or 3 spikes after our principal. That's a huge frequency suppression in response in the palette, getting more power on frequency. And if you go and put a low pass filter on it, it's going to take and only have to capture this much garbage versus this much garbage across the frequency band. It's just food for thought. Just food for thought. So let's come on over here. Let's get down here and let's go take a look at this. In all fairness, the hottest point in the pallet, which is the flyback resistor, is 154 degrees. And our output transformer that was in the 240s is now 147, 144. That's a 100-degree difference in transformer temperature in operation. And that's with no air on it. And this has been an uncutaway, have not stopped since we first keyed it, timeline and video reference. You ever see, like when we were in grade school, the two dorks in class would get in an argument and they would put themselves into what I call a sissy fight? That's where they close their eyes and they throw their hands out there and they slap fight at each other because nobody's taught them how to make a fist. That's what I think about when people show up in an argument and they say, well, I've got such and such education, and you can see them like tightening their tie, like, myself, am so important. because I went to school and I did this and I got my degree in such and such. Okay, good for you. It is what it is. I laugh at people like that, and I think it's a laughable argument. It's very pompous, and it's very arrogant, it's very demeaning, it's very disrespectful, it's very rude. I just do me. I don't worry about the other things. Now, an answer to that is, what are my credentials? I got 10 years of experience plus working on stuff like this, fixing other people's products, and demonstrating without a shadow of a doubt how to make them work better. So you take that for what it's worth. It is what it is. I don't know. I could stand here and say a lot of negative things. I could be an angry person, and I could take a lot of this personally, and I could really get upset, and I could say some ugly stuff. There's no point behind that. If I was to get into that little adventure, I'd look like one of them little sissy bitches that stands there on the playground going, "Stop it! Stop it!" I'm not that kind of guy. I'm not. So when another technician asks another technician in a public forum about their product that they produce and their equipment, and the only response is, "I'm going to go call the playground attendant, and then I'm going to pull out that I've got official education in something," I don't think I need to say anything more. I think everybody's got the words in their mind of what I'm thinking. Look, this is what it is. It's a very simplistic, very cheaply produced, very cheaply manufactured piece of equipment that is incredibly broad-banded and is very dirty, in my opinion. And I'm not going to say don't buy this, because then I could be in a lot of trouble for suggesting to people that it would open me up to some stuff that I would not be interested in getting involved in. I'll say this much. This is not something that I would invest any of my own personal money into to buy or use, and I would definitely not want to use this on the air because of, well, its characteristics of being so harmonically filled, right? So I can't get behind this product, and I can't say that this is great. And in the same breath, hey, we now all know how to fix it to make it so it's going to work anywhere we want to use it. You can take the same transformer spec, and by changing your capacitance values, you can make this work anywhere on the HF band you want. Not just on 27 megahertz, not on 10 and 11 and 12, but you can easily make this work on 40, 20, 80, 160 if you choose. The point is that this is a flawed design. I mean, personally, this is not anything that I would invest any energy into. That's my personal feelings about it, okay? You do as you see fit for your own needs and desires and wants in the radio world. Because when we boil it down at the end of the day, it's just radio. It's just radio. Now, if somebody's got to get on the phone and call the hall monitor, so be it. At the end of the day, honest, straightforward, and it's just my job to fix the equipment. Guys, I've got to go. I got a ton of stuff I got to go take care of. This weekend, I decided I'd invest probably about 5 or 6 hours of my time and come thoroughly address some of these units. Hopefully this will help save people from a lot of headache and frustration, sadness, madness, anger. I can think of just a dozen people out here in the Northwest that this is going to help that I've personally met. It is what it is. No, if you call me on the phone, I'm not going to tell you what the capacitance values are. I think it's very clearly put forward what you need to do and what you need to try and play with if you're going to want to learn how to modify these to make them work better for you so that they'll actually be usable on frequency. Good luck playing, guys. I'm done on this issue. You're going to see 3 or 4 more of these videos come out in the next couple months where I've got to remodify and, repair. We'll use the term repair these pallets to make them work properly. So on that note, I got to run. Gentlemen, I appreciate everybody tuning in, and Like I say, usually in every video, I'm going to say here at the end, if this is your first time watching, take a minute, click subscribe. Doesn't hurt nothing. I'm always doing crazy shit like this. Lots of big projects I've been working on in the background. Lots of them. If you've seen this channel before, and this just means you're a repeat offender, and I say welcome. I say thank you. We'll see you again on the next video. Big projects coming up here in the next couple weeks, you guys. It's the reason there hasn't been a lot of YouTube videos out, because these are long construction videos. I'll see you guys. Bye-bye.